we generally have SA. And when I say 3D, I'm talking about aerial 3D right now, kind of a flat, wiggly surface. So in this 3D data set or aerial data set, we don't really have this idea of RA or WT. We'll just have some surface roughness that's related to the band that we're currently looking at. We could take this same measured surface, though, and look at multiple bands. We could look at the fuzzy details along the ridges, or we could look at the more periodic spacing, or perhaps the form or the undulations underneath that. And every one of these shapes could have an SA value of its own. So we could have an SA for short waves, an SA for medium waves, and an SA for long waves, and it's still SA. But the notion is that we're going to take our surface and we're going to do some processing. For example, in this case, I'm pushing a waviness filter through the data. We could either look at that waviness or perhaps we could suppress that waviness altogether and look at what's left over. Let's sync those views to make it look like that. So what wavelengths are we interested in when we start talking about appearance? Well, in the world of appearance, we might consider long wavelengths as a different process control and a different behavior than short wavelengths. So this idea, again, of breaking our surface into wavelength domains is going to be super important to connect that to the world of appearance. So we have tools for doing this. Our toolbox has always existed. We have tools for changing a filter cutoff. If we go with a larger filter cutoff, we'll see this waviness flattens out a little bit and more of the shape winds up in what we call the shorter side of the filter. So with the tools that we already have, we've come a long ways in the world of processing our data, but we're now getting to the point where we're trying to target smaller zones. For those of you in the stylus world, you might be familiar with the typical roughness where we would go from, say, 2.5 micrometers of a short filter all the way up to 0.8 millimeters on our long filter, or we would have a short cutoff and a roughness cutoff in the stylus world. That's actually a very wide band in terms of appearance. When we start looking at surfaces with our eyes, we find that narrower bands become interesting. In this particular example on the screen, I have a slightly narrower band. I've gone from 8 microns of a short filter up to 250 microns of a long filter to better isolate this shape. So that's another new piece to a lot of my stylus using friends out there is we're getting more specific. We're dialing into a narrower range. It's like we're listening to a symphony and we're interested in a narrower range of frequencies. Maybe we're just pulling the trumpets out of the symphony and we don't care about the tubas. So we're getting more targeted and getting smarter about what matters. In terms of this targeting, I think the aluminum foil example is one of my favorites. By the way, I'll give you come up for air here, Edgar. Is there anything in the chat that I might be missing?
Not yet, but a reminder, you're welcome to put your questions in the chat and we'll try to feed them in.
Awesome. Yeah, even if you have something nasty to say, any press is good press, right? So feel free. This is a cool example because if we look at the two sides of aluminum foil, one side is obviously more dull than is the other side. A typical roughness analysis, though, might only see it as perhaps 25% rougher. And you can see the shiny side versus the dull side, if you will, with this data below. So that again is a wide bandwidth looking kind of at all the wavelengths in the surface. And there's not a huge difference. 25% is not a big deal. But if we start thinking about what your eye perceives as dull, something different happens. That idea of dullness, the surface being frosted or hazy, actually occurs at very, very short wavelengths, wavelengths shorter than what your finger can typically feel. So if we dial this into a very short domain, 2.5 micrometers up to 80 micrometers, The shiny side versus the dull side start to look quite different. In fact, we'll see more than 2 times the roughness on the dull side. So our eye is sensitive in this word dull or frosted in the very, very short domain. And that's what the aluminum foil difference is. Aluminum foil is still quite rough on the shiny side, but the dullness comes about from a very short wavelength domain. All right. So we get the idea, though, that as we start talking about appearance, we're going to have to narrow down our region of interest. Like this is a very narrow band of wavelengths where the difference becomes very obvious between these two surfaces. I'd like to scale back out to a larger domain, though, and talk about our tools that we use for getting at these wavelengths. Particularly for my stylus using friends, we just kind of keep our knobs dialed into 2.5 microns of short and 0.8 millimeters of long, and they're kind of gunked into place there if they are physical knobs. But to start exploring our surface in more detail, let's look at this picture or this data set from this key pictured here on my screen. And please don't grab the screen of that and use that to unlock my garage. I'm trusting all of you now. But we can see this milled zone where my mouse is here. And here's a measurement of some of that region. In our traditional stylus world, we would have set a short filter of 2.5 microns and a long filter or a roughness cutoff of zero point 0.8. And we might have turned on a parameter like an SA or an RA and put a plane through that. This leaves us with a filtered data set like this. We can look at that through a different set of eyes, though. We can look at that through a set of wavelengths that the surface has. The surface has a very strong wavelength here relating to the sine wave here. So this is wavelength versus amplitude, or amplitude in the y-axis. We see a very strong spike right here at a spacing of about 0.87 millimeters. Magically, that would be the spacing. Let's turn off the Y and turn on the X. That would be the spacing over here. So this representation of what are we filtering into our filtered or roughness information versus in black, what is actually in the data is a really powerful starting point. For example, let's pull up the primary data here and the filtered data over here and start watching how we're processing. Tell you what, let's just do form removed and filtered and have a play now. Playing with data is my favorite thing, by the way. Currently, my filtered data is the standard roughness band, 2.5 microns up to 0.8 millimeters. But what if I move my cursors over here and I got real interested in just this sine wave running through the data? Let's choose that zone and put a filter right there. We will use those cursors as a filter band and filter into just that shape zone. That's what we have if we include this domain of wavelengths. We've taken this milled surface with lots of information and filtered into just this one wavelength band. Now that
This
is a
that
weird
is a
set of.
nice software feature. I'm so impressed.
Thank you. I appreciate
It's
that.
great to
It's a
see.
great teaching tool.
Yeah.
I like software that teaches, so thank you. Now let's say we do want to understand what's left over. We've targeted the lumps here, and lumps is a really techie term. I love that, but hey, we're talking about appearance, right? So let's look at the fuzz that lives on top of the lumps. I'm going to put the cursors in the short domain and use those cursors as a new filter band. Well, now you see we've removed the lumps and everything left over becomes our filtered data. In this world of just the fine details, I have an SA of 1.1 micron. Let's go back to the long domain and use the cursors there. I have an SA of 2 microns. So we're seeing different roughnesses depending on the domains we're choosing. And absolutely, I agree with you. This is hands down my favorite software tool I've ever developed. It's just way too much fun. But it gives us the ability to work our way around a surface and target different things. For example, physical touch. We can touch surfaces and some feel nice and some feel jagged. Well, if we have comparable surfaces to measure, we can filter our way around and decide which zones are highlighting that difference in touch. Quick word on this, by the way, if I use the cursors for a filter band, we end up with some really funky numbers. So I would look at this and say 0.24 to 0.19. Yeah, let's make that friendlier. And when we report it, maybe now we would go to 0.25. And instead of 1.91, let's make that 2 millimeters. And now we have something that we can share and other people can use. But yeah, super powerful tool for exploring your surface and understanding in the midst of all these shapes, what am I seeing? I'm going to pause here again, give you a chance to check the questions and comments. If you have a question, throw a question mark out and we'll wait for you.
Yeah, I did get a question in a side channel here. How do you get the shape out of the way on a complex surface so that you can see the roughness?
That's a terrific question. And there are ways we can do this. And let's look at a complex shape for a second. What do I have? I've got complex shapes all over my life. There are a couple of tools that are really popular. Let me grab a gear tooth. That's a fun, complex-ish shape. Gear noise, gear waviness demo. So this is a gear tooth. It's a pretty wild shape. I'm gonna clear out all my settings. It doesn't look like much when we measure it. It just looks tilted. But if I put a plane through my gear shape, like measured gear surface, we can start to see that the plane doesn't fit very well. See, the plane in glass is kind of diverging from the edges. And when we level that plane, we still have a lot of error left over. So one of the most common tools people will do is they'll jump to a fourth order polynomial. The fourth order polynomial, let me go back to this previous view. So when I turn it on, you'll see the difference. So if I go to the fourth order polynomial in X and Y, it gives this reference geometry some flexibility to land in the surface better. And now when we remove it, we have texture with perhaps some waviness hiding inside. Fourth order polynomials are super cool, super powerful, but I'm also very cautious because as your data gets larger and smaller, the curvature is going to move with it. The size of the image is going to affect the curvature of a fourth order polynomial. So perhaps a better solution in today's world, instead of a fourth order polynomial, is to use a plane and then go to our filtering itself and use something like a second order filter, which tends to follow better. So your mileage may vary. I point this out to say there are a couple of tools that are available. So here I've leveled with a plane and my filtering is now second order Gaussian, and that second order filter follows very nicely as kind of the waviness surface, and we can suppress that and get to a filtered surface. So a couple of tools that are available. Hopefully that helps. I'll let you catch that, Edgar, in case that was good
Great, thank
enough.
you. Yeah, yeah,
You're,
yeah. Thank you.
yeah, you're my voice of the audience today. How do you like that?
All right, I'll be there.
High pressure, right? So once we've established this ability to zoom around and look at wavelengths, we really do need to ultimately figure out which wavelengths relate to the things we're seeing with our eyes. So in the world of paint, painted car bodies, and we're dealing with a substrate that's going to be painted, there are a lot of fun words like gloss and haze and clarity and orange peel and waviness. Our task becomes relating geometry to these words. And I think Don Cohen was on with us, and I want to give props to Don for working with me on this. But this is a typical car body panel. On the top left, you'll see a fourth order polynomial removed surface. So just like the question set up nicely, here's a surface where we've removed the fourth order polynomial, and everything left is going to be surface texture. Now this surface is scaled 0 to 5 microns, and over here on the right, we see individual bands of wavelengths. So I'm going to scale this side up a little bit. Let's go 2 microns to 2 microns. Yep. And we'll do the same here. And slows down my mouse clicks. This surface has several wavelength bands of interest. And I'm going to scan through those bands and watch this plot right here change as we go from a short band of wavelengths, which may be haze or clarity kinds of things, into longer bands, which might get us into something like orange peel or that kind of thing, figure
I,
kind of shapes. Go ahead.
I do have a question on that. Are there standards that define words like gloss, haze, orange peel? There, do we know
They
what
are
those are?
they are very jargony at this point. I have not seen anything. If you would unmute Don, if he happens to be with us, he might actually have some more insight on that. He's spent a lot of time measuring these. Don Cohen, are you in the chat?
Hi, Don.
I'm
I have
here. Can you hear
allowed
me?
your. There you go.
Yeah, we've got you, Don.
Okay. Yeah, that's actually a good question. There's a lot of different instruments out there that say gloss meter and haze meter and all that kind of stuff, but I'm not aware, and that's just because I'm not that deep into it, like an actual spec that says it's these spatial wavelengths. I think what you'll see is people define their own bandwidth of spatial wavelengths of what they call haze and gloss and all that kind of stuff. And I'm sure we'll hear later and hear about some other instruments and what the bandwidths are. But again, I'm not the great expert in that, but I'm not aware of some kind of ASTM standard that says haze are these spatial wavelengths. The concept of spatial wavelengths is really just getting introduced now, into the world over the last 10 years.
Awesome. Thank you, Don.
Okay.
So a
Yep.
couple of things we can notice when we do this is in this surface, the short wavelengths are all very directional, like the rolling of the metal. And then as we get into the longer wavelengths, things become more random. But unpacking this a little further, on the lower left, we see a graph in blue of the wavelengths in the surface, and then the colors and this transmission curve showing us kind of where we're sitting. And we can go a little bit farther with this even, and people are going to a point of looking at parameters across the bands. Is it rough in a certain band and relatively smooth in a band next to it? But this is bridging that gap from topography and geometry into things that our eyes like to see, beauty and appearance. So I'm going to cut out at this point and hand things off to Erik to show you some very cool ways of getting to this kinds of data. I'll certainly hang on. I'll be watching the chat. And Erik, it's all yours.
Yeah, thanks a lot, Mark. Let me share my screen here. Yep.
Yep, you're sharing.
So yeah, what I'd like to talk about is, specifically, for the topic of our webinar now, an application where surface analysis really matters and, can make a big both financial and quality difference to an industry. And then, how to get that data and make sure that that data is worth analyzing. And the specific application here we're going to talk about is coding, and then particularly talking about coding in the automotive industry. And it's really a very critical process for the industry. Coding actually accounts for 30% of your total vehicle production costs, which when I first heard that astounded me, and might astound some of you guys. But that's mainly because it's extremely energy intensive. There's a lot of capital involved in it. The chemicals are not the nicest chemicals, and so there's a lot of environmental costs as well. And it turns out that the paint process for a vehicle is a zero yield process. Now, that doesn't mean everything gets scrapped, but there essentially is no vehicle that goes through the line that doesn't have at least some touch-up work, and sometimes entire vehicle panels need to be replaced. And customers are very demanding of color and texture and paint quality. There's been more than 25 recalls just this in the 2000s just over paint quality. And for a while, it was one of the #1 complaints about the Tesla electric vehicles. And the goal should be, don't keep on with the process if the part is already known to be bad. And the challenge has been that until recently, um, the coating process was never really quantified until the very end stage. You did your final paint and you did your clear coat, and then you looked at the quality. And if it was bad, then you figured out what might have happened. But there was no checks along the way. And so, really, the entire process is very ideal for comprehensive process control, via, factory 4.0 type methodologies. And, just to give you an idea of a bit of the complexity of the process, you have multiple layers going on. Each layer affects various vehicle properties, be it weather resistance, the overall appearance quality, rust proofing, chipping, susceptibility, etc. Each of those layers affects the appearance. Every layer is influenced by the prior layers. Sometimes defects can paint out, sometimes not. And then it's increasingly complex now because, especially with new vehicles, there's increasing numbers of materials, right? Cars are no longer just steel. There's steel and aluminum and plastic and composites, and all of those different materials have different fundamental properties and will paint differently. And prior research, with folks like Don and Mark, and led by people in the automotive industry, such as Alex Pete, really have determined, key system requirements, right, in order to quantify what's going on with the paint process. And so the eye is actually, to Mark's, presentation, sensitive to structures up 4 or 5 millimeters wide. And so you need a very large field of view because you want to be able to sample at least some of those structures, multiples of them, to have something that's statistically significant. Concurrently, you need very high lateral resolution because in terms of haziness and dullness, your eye is sensitive down to very small wavelengths. So you need, 15 micron-ish lateral sampling. Paint is very smooth. So you need nanometer level vertical resolution to look at the final paint and clear coat. But then the initial substrates are quite rough, sometimes over 2 microns rough RA, and they're curved. So you need high vertical ranges and you need the ability to measure rough things. Ideally, your system is going to be portable. It might be handheld, so you just walk up, as you see on the right, measuring a car hood or a car door in that case, or it's going to be robot mounted in automation. Needs to be material independent, able to measure all those different materials. And already, there's 10,000 different paint colors in the automotive world alone, and about 1,000 a year are added. You want it robust to difficult environments. We're not talking about a lab. If you need to cut up your car and bring it to the lab, that's time consuming, that's difficult. And then you want instant results. It needs to feed back into the process. Otherwise, it's no good. If it's a week later, you've potentially, cost thousands of dollars in terms of not controlling the process. And it's very obvious why substrate, or why automotive manufacturers are so interested in topography, right? You see it. It's the thing, everyone sees first on a vehicle is quality. And this is actually a slide directly from our partners at General Motors. And in this case, we're seeing an aluminum front door and a steel fender panel. And obviously, it looks extremely different, and that would be unacceptable to customers, right? You're advertising a very high-end vehicle, like you see on the left, and it's, beautiful and tasty. And if the reality is someone gets something that looks terrible, you're going to lose a customer. And, a little bit about 4D, we were approached to help solve this problem, because of our capability with production line 3D metrology. Our entire foundation of the company initially was nanometer scale measurements of telescope optics, which are very long distance. And if you guys have been paying attention to the news, what you see in the upper right picture is the James Webb Space Telescope under test. And the instrument doing the testing is on the left with the two gentlemen on either side of it. And, tens of meters away is the telescope that needs to be tested to nanometer scale. Turbulence, vibration, all of that needs to be eliminated from the measurement process. And so we took that, the technologies involved in doing those measurements, and then have applied them now to industry to make vibration and environmentally immune 3D measurements on the shop floor. And a couple examples of that here I'll show you is on the left. Turn off the sound here, but you see one of our handheld instruments actually. Uh, it's got a power supply in the backpack, a Microsoft Surface Pro, and it's able to do instant 3D results, right? So you walked up to the part, got some feedback from the camera, took a measurement instantly, and is able to get 3D measurements, look at different areas of interest, find defects on a part. And, that's a really empowering thing for folks. And then, another example on the left, same instrument, just being used in this case on a benchtop. But again, you just go up, you click a measurement button, as you see green in your live video in the upper left there. And once you do that, you get an instant three-dimensional representation of the part. In this case, is a nicked blade edge, and you can quantify that, right? So we were asked to take that kind of capability and see if we could do that, again, to automotive paint. And really, this is an evolutionary product, right? So, way back in the 80s, the Wyco RST Plus was introduced as, a 3D microscope, and it was a great lab-based instrument that eventually became very automated with auto staging and autofocus and everything else, but still unable to bring the measurement to the part, right? In order to do these measurements, you use measurement labs like Don has, where he can take sections of parts and stitch them together and do measurements. And then what we really did was productize something, and you can see an alpha version of it on the upper right, and then the final version in the lower center, that's small and portable, and you can just bring it to the part and do measurements, on the shop floor, not in the lab. And I'm not going to dwell on system specifications. We kind of talked about what you needed, but yeah, 16 millimeter field of view with 15 micron sampling, better than a nanometer of vertical resolution on smooth surfaces, about a 6-inch cube in terms of system size, and quick measurements, 3 to 30 seconds for both measurement and analysis, and some built-in analyses, but also because we're not experts in the spatial domains and everything, just a very easy port of the data to Bandify 3D. So you can take a measurement, click a single button, and get all the different spatial frequency results that Mark was showing you. And the goal is fingerprint the whole process, right? Scrap bad material before you spend additional time and money bringing it to the next stage of production. So measure the sheet metal, see if the steel has defects, see if the aluminum has roping, which does not paint out. Look at it after the stamping process, after closure, once it's assembled in body and white, pre-paint, and then throughout the paint. And at every stage, you want to use the same instrument, if at all possible. And that was our goal, right? Because cross correlation of different metrology instruments is notoriously difficult. especially if you're talking about different spatial bands, right? Every band is going to be differently sensitive on different instruments. And so to use 2 or 3 or 5 different measurement techniques across the different stages, it actually becomes, almost impossible to do proper process control without, months or years of correlation efforts trying to figure out the nuances of each system and how they change in environment. And, again, the goal, replace subjectivity with quantified criteria. So a lot of folks are still using eyeballs and fingernails to measure things, and visual methods just don't cut it. And even basic roughness measurements often don't. So in the lower left, you see, 4 different bright field images of steel, and you really can't tell one from another. But if you look at a very specific spatial frequency band, and I forget exactly which one this is, I think it's the long frequency band. Those 4 coupons look very different.
Erik?
With Yes.
Yeah, a couple questions for you. The first one has to do with instrumentation. There are instruments that measure paint. Do they not also measure substrate?
Yeah, typically not. The most common instruments for measuring final paint quality really require the shininess of the final paint. And so they're only able to measure it at the last stage, and they're fundamentally incapable of measuring a multi-micrometer rough raw steel substrate. And
Interesting.
so
So,
there are 3D microscopes that can do it, but again, those are kind of lab based, and ultimately because of that, they're destructive. So in terms of a portable instrument, we were approached because there was no commercial solution out there.
and kind of a related question is from Julie. Can you find roping potential before stamping?
Yeah, and that's exactly what we're doing here. So the image on the right, that aluminum exhibits roping. You can see roping is, for those who aren't familiar, these long striations that happen from crystallization in the aluminum as it's stressed, and that's going to look almost just like that after final paint. Whereas the coupon on the left, with an SA in this particular wave band, almost 7 times lower, that'll paint just fine. And that's actually one of the early applications of this product, because that's been a real problem with industry as they move to more aluminum and try and lightweight product. And the goal then is, figure out the SA threshold that matters in which wavelength, and scrap the part, scrap the material before it's ever, stamped. And, again, so the process, I won't dwell a lot on this. We've been talking about it. Measure it. Use a program like Bandify 3D to filter the data. So there's our initial measurement with all the wavelengths. Break that into different bands, which you see in these various plots in the upper right. And then from that, you can actually plot out SA of each band, and you can determine what the fingerprint should look like. So you don't need the same SA everywhere, but you can determine what passes and fails for each band and really quantify what's going on with the process. And there's both built-in bands into Bandify, WA, B, C, D, E, and then there's also customizable bands that various manufacturers have found better match their process and their quality needs.
I think you're touching on the question that did just come up for both you and Mark. What's your experience with band analysis with other parameters such as wear and or friction? Have you found any good correlations at different bands of a specific roughness profile?
Yeah, there certainly are. I don't have any examples of wear and things here. It's actually, again, both Mark and Don Cohen are more expert actually, in the analysis, particularly I know for wear. I know Don has taught whole courses on how to examine wear and what different things matter in terms of looking at bearing ratio parameters and other three-dimensional parameters, some of which are not necessarily wavelength based, but more contact area based. So yeah, there are definitely ones that matter, and I guess I'll refer folks to Mark, and Don is from Michigan Metrology, so you can look him up as well for maybe a more expert opinion, or we can talk a bit if we have time at the end here. So yeah, again, talking about wave bands, Mark was talking about standard filters, right? So a standard, 0.8 millimeter filter, no differentiation really between the worst of the worst and the best of the best in terms of what the surface looks like. But using a long wave filter, again, now we have high differentiation, and you can clearly, see the roping in this case, no to scrap material. This is just a slide, again, just showing, Mark showed some examples of, different surfaces. These are all surfaces used in the automotive process, and it just shows in an unfiltered sense how vastly different surface morphologies can be depending on material, and even like within plastics, how it's machined and how it's produced. And so you can see here, if I have all these different materials and they all have to look the same after painting, I'm probably going to be in trouble, right? And so they might need pre-processing or additional steps in order to ensure uniformity. Another example, again, the substrates on the top kind of visually look the same. They all have the same vertical scale from plus to -2 micrometers. You can see, yeah, some differences, but they're fairly subtle. But then when you look at the final clear coated panels from those substrates, they're pretty different, right? In terms of, you can even just visually see the lower right panel has higher frequencies and less pronounced highs and lows than the one in the lower left. And so we need to figure out, what causes that so that we can control process. And you can do that through fingerprinting, right? So you can look at various bands, and in this case, I don't have the actual spatial parameters here because it's kind of proprietary. But when we looked at the first band and looked at RA or SA between the substrate and the final clear coat, not much correlation. And so that would be bad in terms of trying to control process. But looking at a different band, very high correlation, of results in terms of, initial substrate answers versus final clear coat roughness. So measuring in that band allows you, again, to know whether something's good or bad and predict problems before they occur. And a lot of times as people use 3D, the goal is not to have 1,000 numbers that you need to pass in order to control the process. Pick the ones that matter, but maybe store all of them, because sometimes just storing everything in the database, when eventually a new problem occurs, you can go back and say, okay, it wasn't predicted in this case maybe by band 2 that I was using on a daily basis, but some other band that I was storing, I can say, oh, that one changed, and that's predictive of this new problem I found. So fingerprinting data from 3D results is an extremely powerful tool in the background to help more quickly solve future problems that you don't even know you have yet.
Erik, I have a question kind of about how the instrument works. What is the minimum layer thickness that can be distinguished when you calculate SA for a multi-layer coating?
So this is a visual tool, and so we're really measuring whatever is on top in terms of opaque layers. So we will only measure the topmost opaque layer. If there's a clear coat, we would typically want it to be more than about 7 or 8 micrometers thick in order to differentiate between the top of the clear coat and the actual painted surface underneath. But because this is a light base, it's essentially a very portable, vibration resistant microscope with a large field of view. So we need the light to bounce back. So we won't do layer thickness of opaque layers with an instrument like this. And I think this is just about my last slide here. And again, this a lot comes with our work with the automotive guys. The goal here, for us was to help create a single instrument to characterize across all the different types of materials and across the different process stages. So you don't have to worry about instrument correlation. To use software such as Bandify 3D that can allow standardized comprehensive analyses across the various parties in the industry. And then I know folks from GM, from Toyota, from the material suppliers like Alaris and US Steel are working together and, helping the whole industry rise, right? Um, in partnership, right? It's not, that every company is on their own, but if everyone works together, characterize the inputs and outputs that matter, uh, help figure out, what is causing problems from the substrates to stamping equipment, coating materials and equipment. Sharing the info is really going to raise everyone up. And I've been really, pleasantly surprised as we work in the industry at the strong partnerships there are. And that's a little bit recognized here where we have metrology consultants and experts such as Michigan Metrology and Digital Metrology working with uh, folks like GM and the other automotive end customers, and then again the material suppliers, AK Steel, Alaris, etc., and then the material guys from Axalta, BASF, and more. And so, what you've seen in this presentation has kind of input from everybody, and we're hopeful to keep moving forward on that. And with that, that gives us just about 10 minutes for further questions. And then again, here's Mark's email and my email as well. We're happy to follow up offline as well.
Let me open up the Q&A with a couple of things. First, Mark, I don't think we got a chance to know what software you were using, that excellent live demo you were showing there.
Um, Live, I was showing OmniSurf 3D for the individual data sets and the Bandify 3D package at the end that Erik referred to.
Okay, great.
Those are,
And Erik, we have a question on the SurfSpec. Is it orientation dependent?
It is not. So it is designed to measure sideways, upside down, horizontally. Really, the thought is that you can walk up to any part of a vehicle and be able to use the vacuum feet to couple the instrument to the vehicle and take a measurement in situ.
Is this a product which is still in development? It looks like you're still working with partners, or is it available for order? What's the situation there?
It is available for order now. It was recently released. It had been in beta for more than a year, actually, getting feedback from various people, much of which was very valuable. We incorporated that feedback and the product is now released for sale.